Welcome back to the stream. I bring you a cat eating something fish related. I'm sure that's what you're here for. No, it's not. It's okay, we also have electronics. So today's project is still the kind of long-running experiment here to extract firmware from a device over Ethernet by voltage glitching during an HTTP request. So, looks like this. So this is the board inside of a programmable logic controller that we're trying to extract firmware from. That's the microcontroller coated in copper tape and solder blobs. And this is the relocated user interface that would normally be on top of here. I kind of moved it aside so I can still work with it while the thing is open. And the thing that I just added was this board over here. This is a glitch generator that I tested using the... I'd previously tested this using the eval board, configured very similarly to this, and so now it's time to port it over to the real thing. Hey Tuco, you sure are on the desk. Oh man, Tuco sure is climbing everything. I guess I'd better bring the camera over here so he knows, you know. I don't know what Tuco thinks of the camera, actually. What are you doing, Tuco? Oh, he looks nice up there, at least. Alright, so basically I have a start at getting this thing set up for glitching, and so it's usable. It has a clock input coming in from the rest of this rig, being generated by this FPGA. I can generate glitches, I can reset it. I've got a manual reset button over here. So that's all hooked up. The main things that I want to do still, the 3.3 volt rail, the one that's feeding the processor, I added this resistor to separate it, but it's still super noisy. So, I mean, the 3.3 volt rail on this board is noisy because it's got a switching supply and there's a bunch of other stuff attached to it that's going to be generating noise on that power rail. So since I already went to the trouble of separating it and adding the resistor, I'm going to add some capacitance on the microcontroller side of that to just try to reduce the noise. One measurement I have for just how good a job I'm doing at looking at only the relevant power line noise is to look at the, I'll look at the core voltage probed from right here using the scope with a passive 10x probe, and I should see some noise on there that seems to correlate with CPU activity. If I hold the CPU and reset, I should see most of that disappear. And right now I see some of it disappear, but there's still a lot left that isn't really correlated with the CPU, and it doesn't seem it doesn't seem to go away when the CPU is not running any code. So a little bit more capacitance there. I also planned out kind of exactly what I wanted to do with breaking out the 3 serial chips here. So the microcontroller relies on these 3 external devices that it communicates with over serial buses. There's one shared SPI bus that it uses for both this flash chip and this MRAM non-volatile memory chip. And so it uses one set of, in, out, clock, and then has 2 different chip selects. Then over here, this kind of chunkier looking chip is the real-time clock, and that actually has an integrated 32 kilohertz crystal. So, and then I have a handful of free headers over here, basically as many as there were room for. There's a couple on the left that are reserved for ground and some Ethernet stuff that I had already broken out. There's a couple over here in this bank that are actually free, but I don't have a ton free, so I made a little plan for how I was going to use those. These are all the signals I want to break out. So that's a sunbeam. So I've got, so I actually want to get in between the real-time clock and the processor. And there's a couple of reasons I want to do that. At first, I just want to be snooping on the communications without modifying it. But I suspect that the next step here is going to involve disabling the real-time clock and then seeing how it operates when there's just no clock. And then probably very soon after that is I'll discover that I do need the real-time clock, and I'll end up having to implement one on an FPGA. So there's actually an I2C slave core on OpenCores that seems like it might be really easy to use for exactly this. So if we get to that point, that's the plan. So with this, I figured I would split out SDA and SCL so that I have access to both the side of that the side of that headed toward the clock and the side of it headed toward the MCU, and I could just connect them with shorting jumpers when I don't need to interpose. Then there's a bunch of other signals that relate to the two memory chips. So there's the master in, slave out, master out, slave in. Those are the two data. There's a shared clock. And then each of the two chips has its own chip select and write protect going to GPIOs on the processor. So I don't actually have enough room on this debug header I added to break out all of the signals that way. I could add more headers, but I'll start to crowd out. Like, I don't know, I could add a second row on top, or I could add it somewhere else, but it's starting to get a little crowded. However, the flash chip here actually comes in an SO8 package with big chunky leads that I think I can grab onto using micro hooks. So I think I can get most of the signals that I want off of this chip's pins, and that just leaves the write protect and chip select that are unique to the MRAM chip, so I can just break those out. So I think that'll actually work out pretty well. So I think that's everything I had on my list to start with. And once we actually start seeing some traces from this, I suspect we'll get some more information about what to do with the real-time clock. Oh, let's see if I can get Tuco on the camera again. Let's carefully put that coffee somewhere. Oh man, that VFD is really flickering on a particular exposure. It looks like he's looking over at the DSLR picture. Hey, little tiger. Oh. This is a little perilous to have one. So I have like a little IKEA table there that is currently holding the laptop and the tripod, and would have been holding the coffee also, which seems like a bad idea. Okay. Man, it's like I need a different place to put my coffee. Maybe I'll put the coffee on the floor. It can't spill on anything. All right. Oh yeah, it's not on my list, but it's so obvious I might just do that first. I am done with this wire here that was running vCore to these SMAs, and so right now it's serving no purpose other than to gather noise, so I'm going to take that off too. Hey Tuco, thanks for standing on the laptop. You're not going to sit there, are you? Focus. This time I'm just yelling focus at myself. Just the joy of a manual focus camera. Where are you? Hey Tuc. Tuco, where's your bolt? Tuco, where is your nylon hardware? Cat, show me your favorite stuff. What do you want, Tiger? Show me your thing. Those are SMT capacitors, which are for me, but maybe I'll just get your box of bolts from over here. You want one of these, boy? What a weird cat. All right. Did you find it? Did you find it and then leave it way over there? Oh, what a weird cat. Okay. All right, weirdo cat. This SMA connector is going to look huge next to the soldering pencil. What even angle is that? Did I mention I live right next to both a train station and a fire station? Let's have that turned off while I solder it too, just because, you know, let's not be shorting V-core. Bloop. Tuco's just like circling around behind me. Maybe you just need to sit the camera somewhere far away in wide angle so it can see Tuco orbit me. Oh no, conductive debris and bent tweezers, two of the worst things. Tuco, are you keeping the laptop warm? Alright, so then that goes over here. And that's the one I want to take off carefully. Tuco, I hear you sitting on that keyboard. That was pleasant. Tuco's going to be modifying all my data sheets. I'm going to go over there and the title of all the signals will just be replaced with commas or underscores or something. Okay. I was going to refer to a data sheet before I work on this part. Let's add those capacitors. I think that'll be easy. Actually, I think the first subtask in adding the capacitors is I actually want to give myself a better ground around here. Because right now I don't have much of a good ground and a lot of signals So like for high frequency stuff like this, the little alligator clip on the scope probe is absolutely useless. So I have to have a ground nearby that I can put the spring clip probe on. Tuco, that's super annoying. Oh, buddy. Ulysses in chat says, don't you live next to a prison too? Sometimes there's a honk that sounds like a prison gate. No, I think that's actually the loading dock at the... There's also a FedEx facility across the street. I think that's what the honk is from. Because they have a bunch of loading docks, and I think some activity that they participate in involves honks. I mean, there's also other loading docks around here, but the FedEx one is the most within earshot. And also pretty active. I mean, I can see a bunch of FedEx from here. Actually, there aren't a lot of trucks around because I suspect they're mostly out making deliveries, but there's room for a lot of trucks. So, oh, that cat. Okay, let's figure out where this ground goes. I think we don't have super obvious spots, but I think one of these test point looking or possibly capacitor-ish pads lead to the ground plane. So let's find something in there that is a ground close to the CPU. Cat butt induced document changes. Yeah, that's danger anytime cats are around. All right. Ground. Oh, there's hot glue on everything. I think I might do a mini project of adding a power light to my hot glue gun so that it's easier to tell when I leave it on. Let's see. That seems groundish. Is this one 3v3? Yeah. I think this used to be a capacitor that I took off. So that might be a really good candidate. What is this thing? No. Any of these? Yeah. These outer ones are ground. Inner ones are presumably some other power rails. Okay. Well, let's just add some copper foil there to make this a little easier to debug with. Copper. Cat says Control G. Yeah, exactly. How much of that fits in there? Not much. I think I want to focus on this one. Whew, that's tight. I'll need to trim that still. Let's just have a little bit of that. I have a couple of different spools of this copper tape. The one I'm using right now I got from an electronics store a while ago. Fry's Electronics. And it's really thin, and it seems to be pretty good quality. It was kind of expensive for the amount I got, but... Then I also have some that I got like from a craft store for doing stained glass. And I've been meaning to test the conductivity to see if it's actually as good. Because now I've got this superstition where like any projects I've used that particular copper on, I'm like, oh man, maybe that was the source of my that particular bad connection or something. But it's probably fine. So what I'm going to do, I cut a little piece with a chunk out of it. Now I'm going to fold over the end so that I have copper on the bottom that I can join to that pad. Still a little too long. I don't want to cover those vias because I don't want to risk shorting those out. I guess I could cover that whole area of the board with Kapton tape. But I might want those vias, so I don't really want to cover them up either. I think that's what I want. Let's put that on. Ooh, that is covered in gook. Just tinning this a little bit. Go, little soldering tip. Oh, come on. There we go. That's mostly what I wanted to do. Come on, now I'm trying to eject. Get out of there. Let's clean that off a little bit. Still a little overlap on that via, huh? Well, I'll put some Kapton under it anyway. I don't think I got myself too much in the way. Ooh, that adhesive stuck a little faster than I expected. Non-conductive object. And a little piece of plastic here. There it is. Put a little bit under that other via too, just because I'm concerned. Some of you may have noticed that this would have been easier to do in the other order. Well, maybe I'll just bend that so that that's not going to be a problem. Adhesive. Tube of super glue might have gotten put away. And I don't want to super glue that. That's gonna get all stinky and gross as the board heats up. It's tempting to add a tiny bit of epoxy, but I might just see if I can get away with not securing this until I add some capacitors. That is really weak. Yeah, I'm going to add just a tiny bit of epoxy. Oh, Phil has a good suggestion for super glue and baking soda instead of epoxy. You know, I've seen that suggested a lot. I've been meaning to try it. I haven't actually found, I don't know, I guess it seems like that works if, I guess what I'm trying to say is usually when I'm using super glue, it's because I want it to seep into really thin cracks in something. And so I don't know how that works with the baking soda. Like in this case, I feel like I would have had to put the baking soda in between the pieces somehow and then squeeze in the super glue, and there wouldn't be enough, I don't know, I can see how you can make like a filling out of that, but I don't see how that applies to making a quick kind of surface-on-surface bond, I guess. That's kind of what I wanted. I just want it to stay a little flatter while the glue dries. Oh, I'm going to have to scrape off this epoxy. Got a little epoxy on top. on, stick. No. Stay down there. What can I put on there to keep it down? Balancing objects on this thing. Just want a little pressure in the middle. Well, maybe it's dry enough now that I don't need to keep fussing with it. Well, it is still pulling up. Just going to go grab that alligator clip contraption I have. But it's possible that I've manually fussed with it enough that it's cured to the point where it can hold itself on. Ooh, the epoxy is definitely getting stiff. Okay. Stay down just a little bit longer. Okay. Let's see if that'll stay put while I find some capacitors to add. Oh, there's a question in chat about what kind of epoxy I'm using. This particular is just some random 6-minute modeling epoxy. This happens to be Great Plains brand, but does this have any more info? Not so much. Let's see. Oh, we have some 10 microfarad ceramic, which is interesting. 50 volts. Let's try some of those. And 0.1s if we feel like it. Nanofarads, good classic for this. There's some like 1 microfarad in here too, and I think that'll get us started. So I also want, man, maybe I should just run another piece of copper tape from kind of next door to this up to that resistor. I don't really want to cover anything up, and that's starting to cover up like that resistor array there, but I mean, actually I know what that is, and that's just like pull-up resistors for the SPI bus, and I don't really What I don't want to cover up though are any of those pins, because I do want to have access to all the processor pins. So, you know, I think that's what I'm going to do. I think I'm going to try to put something to the left of this copper tape. Oh. It's also potentially easier to just do this in 3D and stack some capacitors kind of near where I join the copper tape to the board. And then just run a wire from the other end of that stack up to the resistor terminal. That might be the easiest thing to do. So let's plan to have a 10 microfarad, a 0.1, and a 10 nano, and put the smallest in the most prime location. So can I solder this without it turning into a pile of toxic mess? I just want to heat up this end a little bit. Okay, kind of. I really don't think I should add a bunch of flux right now while the epoxy isn't quite cured. Okay, got a little copper sandwich there. Plenty of solder. Little tweezers. Where is the cat? Oh, I see the cat. He's in a great location. Great. Everything is fine. The cat is happy. All right. One capacitor. That one's floating a bit more than it needs to be. Okay. It's a little more down to earth. Still not shorting anything. That's cool. I think those two pins nearby are Ethernet LED related. All right, next, 0.1. should pre-stack these. The lack of anchor here is annoying. The surface tension is almost enough to hold this capacitor up. Alright, and 2 capacitors. Solder the tops together so that surface tension will be on our side. Yeah. Alright, let's see if we can get one more on there. 10 microfarad. Ooh, these are chunky. This is a 1206. It might need to be stacked at a bit of an angle. Let's try a little bit of solder right there if we can. Come on, stick. There we go. Just a little bit of sticking. Don't want to heat up the epoxy too much. And tinning the other end of the capacitor. Okay, almost. Okay. That's better. For a value of better that I have chosen to be acceptable today. Let's run some... I think I want to just run some like relatively thick magnet wire up to that plane. What do I have? I've got 32 and 40 gauge on the table, but let's see if I have something slightly thicker for this job. Yeah, 22 gauge magnet wire should do it. I mean, granted, the actual thickness at this level doesn't matter too much for the super high frequencies, and 22 is actually kind of stiff. Yeah, that should be fine. I'm not going to bother optimizing this wire for flexibility given how little it is. So I want something roughly like that. Start out just tinning that a little. Oh my god, Tuco is out of frame. wood burning. This is not the fastest tip to solder or to a tin magnet wire with, but it gets the job done. It's interesting, not only am I burning the wood, but transferring some of the red varnish to the wood near the ends. There we go. That's what I wanted. Alright, let's flux this a bit. Okay, we can do this. Okay, this next part is going to be delicate. Who has the air horn around here? I don't even know. There's just so much going on around here. I don't even have any idea what business the air horn would have, but it probably has some. This is when I really want more than one pair of pliers. I mean, I have other pliers, but I guess I need more that are like this pair because I really like this pair. Although maybe one that's even smaller would work for this job. I think I can handle the rest with solder though. Let's just merge that solder blob and call that alright. This might tweak this some more later, but this will probably be better than nothing. Ooh, yeah, sucking that heat out. Go, little iron. All right, let's let that be for a bit. So, got that capacitor taken care of. I think, well, maybe the next little soldering job to do is actually to separate those I2C pins on this thing. Oh, Tuco is no longer sitting on top of the laptop with the diagrams. Okay. So that is the composite view of the real-time clock chip that we were looking at. Here's the data sheet. Yeah, the way we're looking at the board right now under the microscope, pin 1 is on the bottom left like this. So we want to lift these 2 pins and then wire up the pins on the chip and some equivalent to the pads that are under them. So we could wire to the pads, but I suspect it'll be easier to wire those to the pads on the microcontroller or something else. There's some vias and there's some stuff on the backside, but I suspect it'll be convenient if we can ignore the backside for this part. So the other diagram I wanted to look at was, I made this one earlier where I traced out the SPI bus on the bottom side of the chip. So these pins up here correspond to the hardware SPI peripheral that's being used for the memory. These 2 shades of purple are the 2 data lines. And so they're being shared between the 2 memory chips. This is the flash memory on the left, and this is the MRAM on the right. And so the same DO, same DI, and yeah, this orange one is clock, also shared. And these are series current limiting resistors, presumably just to avoid I/O contention in the case of software malfunctioning. But the 2 write protects are separate. They get GPIOs over here. And the 2 chip selects are separate. There's one over here, one over here. So we can grab these signals all from the SOIC because they're so large. Then over here we'll want a wire probably here or this big write protect pad. That seems handy. I wonder if this is the other write protect. Don't think I traced that one out. Let's see, we'll want this chip select, which we can get from either this pad or this via or pins on this resistor bank. And then I think that's it. Yeah, actually, so everything is either on this pin, on this chip, this giant pad here, or this via, so that'll be pretty easy too. For this chip, these are the pins we're taking out. Actually, this is not the easiest view to look at that on. Top side. Yeah. So it's a little hard to tell with the chip still on there, but these are SCL and SDA up here. This one definitely runs straight over here to the processor, and I think the other one does something similar. This via here, and I think a similar via under here, go to pull-up resistors on the underside. So yeah, definitely that via goes to, well, let's look at the back side by itself, because the composite might be confusing there. So it's directly under the RTC is this capacitor and 2, what are those, 47K resistors? Yeah, so that's this part of the image. So it's definitely this via. Okay, so it's a via inside a test point. That's why it looked a little weird. And then we've got another via under here. That's a little weird. Yeah, I find that a little confusing, but then this certainly, that via doesn't seem to go anything. I would expect it to be that via. So, I don't know. We can guess about what the wiring is like under here. I don't necessarily want to just take this off because I kind of want all the other pins connected. Oh, I would like to actually take the battery backup off though. That's actually a pretty easy change to make. Let's warm up a second soldering iron for that. This is also on the back side, so let's open this up onto the back side. Okay, all of that stuff off. Alright, so here's the soldering job I did earlier to actually attach these boards. So that's the glitch adapter, and it's got these, oh, that's okay. So, glitch adapter, it's got this twisted magnet wire right over there where there used to be a V-core capacitor. And the other V-core capacitors are taken out. So, actually, I think the easiest place to disable the backup supercap is by just moving aside this resistor down here by the supercap itself. I could also try actually removing the supercap. I don't necessarily want to do that though. This is going to be a little asymmetric, but fine. If I actually touch that resistor with the soldering irons, I'm going to short out the supercap, so in order to avoid that, I'm going to undo the ground, or disconnect the ground of this board from anything else it might be attached to. And double check that. Alright, so this board is floating now, so if I ground the supercap, I shouldn't short anything out. Great. So now, now the real-time clock will still be powered by the regular 3.3 volt rail through a Schottky diode, but I won't have to worry about it powering up in an unknown state if the backup capacitor has charge and, you know, not otherwise. So, I don't think there's anything else I actually need to do to the bottom of the board, so I'll just put it back on. The laptop went to sleep. Okay. Whoa. Oh, hey, Took. Okay, is this a good time to... Yeah, let's continue with that lifting pads plan. Wake up, computer. Wake up, computer. All right. Oh yeah, with that angle in the microscope you can see the two traces leading pretty clearly away. Enough room to put a magnet wire above and below that one, maybe. Oh, there's not any room for my hand in this position. Okay. Should probably find a way to, well, I'd drawn kind of a pin out, which was really more of just a list of the signals I was interested in, but some of these clearly are right next to some pins, so maybe I should take advantage of that. Let's clean some of this epoxy off. Times like this, I kind of want one of those tricks like with the isopropyl alcohol and the hot glue, but for epoxy. I don't remember if this was an intentional anchor point or if I just dripped some epoxy here, because this is a weird place for one. I don't necessarily need to take it all off, I just need to expose the pins, but I also don't necessarily care about preserving it, because it is a weird anchor point. Oh man, there's so much going on. There's like a crew of people working out on the roof right next to me. Yesterday they were hammer drilling into the roof right above the windows in the loft, and it was pretty loud in here. But I suspect they're working hard to make sure that it doesn't leak. Well, I could get carried away with cutting this off, but I've cleared that pin plenty. I just need to clear the other pin. Kind of satisfying. Uh-oh, is that a piece of conductive debris? Is that piece of my knife? Let's not leave that inside the circuit. Alright, I think I can tin these now. Oh. Let's maybe get the epoxy off of those two easy ones that I missed. Whoa, I just remembered I have coffee on the floor. I hope it's still warm. Okay, I think that's fine. So I think it makes sense to use these four for the SCL and SDA here. And maybe I will, well, let's see. Those, I mean, it's probably makes more sense to grab the signals over here than to try to put a wire underneath these pins, even though I think either would work. But soldering directly to the processor is probably easier. I'm also kind of stoked to try 40 gauge wire with this soldering iron tip. I usually use 32 gauge wire, but 40 might be kind of awesome. I'll have to check that out. Oh, this there's a question in the chat about whether this is epoxy or like thermoset glue, and this is definitely epoxy. I've been using a combination of epoxy and hot glue on this project. The hot glue is for stuff that is meant to be pretty temporary, and the epoxy is for stuff that I meant to be a little more permanent. Whoa, and this is the epoxy, but it scrapes off pretty easily. And I'm going to plan to use shorting jumpers here so that when I don't want to interpose between the real-time clock and the MCU, I can just leave these jumpers on. No. Maybe this is why the epoxy. Yeah, I mean, that's a big part of why I often epoxy these after I solder them. Like these, that epoxy is mostly so the pins don't slide around when I plug and unplug things. But after doing that, it's really annoying to rework the connections because you actually have to excavate them. So Well, let's try grabbing those signals over here. So if this turns out to be annoying, I'll want to put them on the underside of those pads before wiring up anything on top. And that sure looks like a short, but I'm pretty sure it isn't. Yeah, that's 3v3. That's not connected, which you'd expect. All right. 40 gauge. .40 gauge is like a thin hair. Like, you get any of that under the scope? To tin it first, but yeah, that's 40. I guess it's still thicker than a lot of those cat hairs. I'm not going to bother tinning it on the microscope because that's just too annoying right now. Okay, we'll be wanting a sufficient amount of flux here. .40 gauge might be smaller than it's worth using. This stuff is really little. But let's see. Just heat this up a little bit. I also want to heat this up and make the solder here slightly less messy. Ow, that's not a solder glob. That's the end of the wire. Okay. Fine. Wow, that was nice. Have another little wire and see if I can get one right next to it without a problem. That iron's a little too clean. Alright, a little bit of solder. No? Okay, that wire is super in the way. Let's fix this. Oh, there is a solder ball. Man, how is that not shorting out earlier? Oh man, what even is that? Oh, that's the pin. Right, right. Because I separated these from the board. I am still not used to this particular weirdness where I lift the pins up into the air and then they disappear because I'm on a monocular microscope. Okay, that's nicer. Slightly better situation for this wire to be in. Okay, now let's put the two neighbors back on. Alright, cool. I don't have to worry about that bottom pad so much because, I mean, I need to verify this with the meter, but it should be fairly isolated from the rest of this now. So, come on. Just trying to check isolation there, and because I've got that resistor connecting, then the meter is still reporting continuity, but the resistance is definitely non-zero. Huh. That's weird. With these two pins that I would have thought would be directly connected, the meter is reading negative 10 ohms. That's weird. I mean, it isn't plugged in. I'm not powering it while trying to read the resistance. That's 0 ohms to the opposite side of my resistor, and minus 10 ohms to this side. I've got to assume that's some semiconductor effect elsewhere in the circuit, confusing my meter. Anyway, I think this is operating correctly. If there was a short between these two, then my whole noise mitigation strategy will instantly become a lot less effective. So it won't be super obvious, but it'll be kind of obvious. All right, back to attaching things. What's that meter? No, that wasn't the meter, that was the iron. What's up, iron? Clean that iron. Usually only see wire this thin on like secondary coils for high voltage transformers, where they just need to stuff a huge amount of wire in there. I think that's what I wanted. Gentle pull test. Gentle little I2C bus. Well, maybe it makes the most sense just to run these two IC pins directly there, and then make these two outer pins go to the microcontroller. Can use somewhat thicker wire here for mechanical anchoring. That didn't actually warm this little wire up at all. Okay, that's just tacking it down very much temporary. Well, I saw the other side. There we go. Depth perception fail. momentarily lost the other end of the wire that I cut off. I'm like, conductive debris, but it's so tiny. Okay, and that one actually goes just right over here. Cut. Alright. Carefully tin those. Oh, flux on my finger. I had flux on the multimeter probes, and then I touched the multimeter probes. Now I have flux on my fingers. Yeah, Tuco's over there, completely uncovered by flux. What's this doing over here? It's fine. It's holding in there. Okay. What's next? I think I just need to break out the write protect and chip select for the MRAM now. So let's go back to the diagram. Yeah, so this diagram. So we can get everything we want from micrograbbers on this chip except for this write protect, which we can get from the big square thing, and this chip select, which we can get from a bunch of places, but the most convenient is probably this via. It's the third via over in this leftmost 220 pack. Yeah. So that is, oops, right here. Back in the real world. I was going to scrape the solder mask off around that via, but it's already probably exposed enough to deal with at this point. And there's a pin we can solder to right there on that resistor. So that should be plenty. And then, okay. So that one next to the write protect was ground, but that definitely looks like they, I guess my assumption when I saw that was that it was part of their factory test procedure, but they have, like, their test points are very different. The test points are smaller and they tend to be on the back. So it's interesting that there'd be just like a big thing there for a write protect jumper. I wonder if they have a version of this where there's like a physical jumper you can put on write protect as a hardware lockout of the state. Because I think this chip holds like state values from the program, not the program itself. Anyway, let's double check that this is the right pin. This is third. Well, this is just pin 3 on the MRAM. Yeah, right protect. So any of that, either the via or that pad right next to it will do. Good. All right, a couple more thin wires. Still rocking the 40 gauge. So really, really don't want to get this stuff tangled. Alright. Now I can just go wherever. So like, that should be fine. What is this doing here? That is non-conductive debris. Thank you. So let's just stick the next two just here and here. Why not? Oh man, these wires are little. Yeah, maybe 32 gauge is the sweet spot for this work. I think it is actually easier using 40 gauge. I mean, for stuff where I'm attaching to something really tiny, I think 40 might be handy. Let's do that without a giant booger of solder on the end of the iron. I feel like I could make my own fuses with this wire. 10 milliamp fuses or something. this is too thick, maybe I'll just order some carbon nanotubes or something. Alright, that'll be fine. I think that's all the soldering. I think we can actually hook up the scope and see what we've got, which I'm excited about. And we can make sure I didn't break this thing by pulling up a bunch of pads and rewiring it. You can see if the noise situation is improved. Okay, clock is still running. Let's try just powering this on and see what happens. Starting up. Seems like it's working. Alright, let's get some logic probes on here. Well, I guess the easiest thing to do is to look at the power. Why have you been stopped automatically? This is what I wanted. All right, so just for reference, you can see there it's fluctuating between no contact with the circuit and contacting the circuit while it's off. And then let's power it up. That looks good. Let's compare that to reset state. Nice. That's looking useful. Okay, we'll take a closer look at all this in a bit. It's a little hard to go through without any landmarks. Although we can already start to see what some interesting frequencies here might be. Well, there's our 27 megahertz. So I think we are seeing the core frequency in here, or possibly residuals from our clock generator. And this larger pattern I would expect to be related to the main loop, but it might be something else. If I hold it in reset, then That is all noise without any correlation that I can find. Oh, that's something. Well, I guess what I'm saying is even at several different timescales, I'm not seeing anything especially periodic, which is good. It means that this is the kind of thing that'll be easy to filter out if I want to. And that's all coming from the program. Sweet. So that's all a good sign so far. Let's have some digital probes. So I'm setting aside 12, 13, 14, and 15 for Ethernet. These two really want to go on either side. Okay. Let's just stick 0 and 1 on the clock. I don't think I had them doing anything especially noteworthy in this setup. And do you need to find a ground? Let's get some micro grabbers. Here's our ground. Can I just clip these onto the jumpers? Yeah. Okay. 2 and 3. Go on these neighbors. And let's see, which of those pins do I need off of the SO8? Most of them. Chip select, data out, write protect, clock, data in. There's also a hold pin for flow control, but I don't think that's being used. I need 6 micro grabbers for this. want reset on this scope too. Let's pick 11 for reset. Is this going to use like all my scope channels except for one? Neat. So let's have, okay, 12 and 13 are set aside for Ethernet. 4, 5, 6, 7, 8, 9 are for SPI. I mean, it's likely I can pare this down quite a bit after getting the lay of the land, but right now I want to just get a lot of information about how this bus is being used. Go, little hook. You can do it. All right. Let's do this knob with the power on. Oh man, putting this many hooks on an SO8 though might actually be a problem. Well, I could just add more headers. Also put these on at more interesting angles. Stay on there, little clip. I just need to put 6 of these on this chip. It's no big deal. You know, don't I have an SO8 test clip around here somewhere? Let's see if I can find that. That would be super handy. not sure where that piece would have ended up. It's been a long time since I've seen it, and I can remember a few places it might have hung out. That's frustrating. Oh, this might be working. Okay, let's find a place to put some more headers on here. How many actual signals am I missing? I need 5 signals off this chip. I have at most 4 free pins on that header. Well, maybe I can just put something right next to this chip. I'm just trying to guess where these are going to be the most out of the way. Maybe a dual row header directly on top of the SO8. Maybe a dual row. Maybe a dual row right angle header, which could be interesting. It is that big. AKA huge. I mean, these signals are pretty low speed, so I can monitor them pretty much anywhere. It's just I don't want to be getting in my way in the future any more than necessary. Oh, that chip has a code printed on it, I think. maybe? I hadn't noticed, but it looks like maybe there's a second printing on top of that chip, like it was customized. Or it might just be some gunge. I could also put a bunch of little sticky uppy wires directly on those pins that I could grab with these probes, but ugh. I could also put a little board right on top of here. I'm going to use the little wires approach. I think that's going to be the least annoying overall. Actually, many of these... Oh. Maybe I'll solder header pins sticking straight up that I can then plug these into. It'll be a little crowded, but I think it'll work out. I just wanted to limit the amount of mess that I make here. Let's take 5 of those. Oh, let's have the soldering iron be on. That might help. And yeah. Tinning one end of these pins. It's not going to be super strong, and I might want to strengthen this somehow. Like hot glue, maybe. Let's warm up the hot glue gun. Yeah, this will want some hot glue so that I don't damage this entire area of the circuit board with what I'm doing. These are nice big levers. A little too close to that left pin for my liking. Oops. Overreacted. No. Now it definitely needs flux. those off temporarily to remove that solder bridge. All right, let's try it again. Just adding solder to try to make a more solid connection with this via, but then it just totally backfired on me. Now that back with the hammer drill, at least it sounds like it's not as close. Okay. I almost had that last time, but they weren't separated enough for me to actually be able to get debug clips on them, but now that should be fine. So I'm going to test this by booting it up and buzzing it out with the multimeter. But before I attach anything to this, I do want to shore it up a bit with some glue. But I'll use hot glue so that it'll be easy to remove later with some isopropanol if I need to. Alright. Let's make sure those aren't shorted. Is this ground? No. Alright. Oh, it looks like it still starts up. Cool. And do we have hot glue? So I don't want this to get too far out of control, so I'm going to make a little bit of a moat, or a little dam for the hot glue out of this Kapton. All right. Let's get some of that glue off of that wire in the middle. Okay, I might need a little bit of cleaning after the glue dries, but that should be a okay compromise between modifiability and not just breaking itself apart. This hot glue inside of a capped-on moat technique is also how I made this little connector over here. So I just built that with the connector in place and then kind of filled it in with hot glue to keep it a little more stable. I can already pull the hot glue off of that middle pin that got a little bit gunked up. Okay. So now, I don't even know if we need the micro grabbers now. Yes, yes, yes. Beep, beep, beep. These are delicate. Delicate, good word for them. Okay, so we've got I2C, SPI, still need to get Ethernet, we've got reset, let's make this one reset. Oh, and trigger output. And glitch. This one needs a ground. Okay, that's a start. Quite everything I need, but we're already picking up some noise. All right. Okay, so Ethernet up there. So I squared C. Let's look at 7. 7, 5. This might be easier with the mouse. Okay. So let's make 7 and 5 the two serial data. Oh man, there's going to be so much on this screen. And clock is 8. Right, and then the two chip selects are going to be, well, let's do flash chip select and write protect, and then MRAM chip select and write protect. So that would be, what are you? 6 and 4. And then three and red 2. And what did I hook all that up to? So I squared C is 0 and 1. And then 9 is my reset, I think. Yeah, 9 is reset, 10 is GPIO trigger. Where's 10? Okay. We don't need that bus. Okay, now let's trigger on reset. Okay. Alright, we have scope triggering on reset. Let's get a further out view of what's going on. Hello, scope. Is that not sampling fast enough to catch it? That's what I'm looking for. Okay. So we can see, okay, so nothing's happening on Ethernet yet, which is the top two. Then these next three traces are the shared parts of the SPI bus. So if we're talking to anything on SPI, we'll start to see traffic here. Then I think this is flash and this is MRAM, but I could be getting those backwards. And so the bottom trace should be write protect, and so we're not expecting to do writing yet. So during initialization, we don't see any activity on that. I forget whether write protect active is low or high, but I think high here means that we are write protected, and so we can't write to the to those chips. So this might be interesting. This activity here, it looks like it's starting to talk to the real-time clock. So let's see if we can get any. You know, I guess I should get this back on the network, since we're going to want to look at the HTTP loop next. So, network. Come back, computer. There we go. All right, now let's see if we can get a link again. Plugging this in. Let's get the everything else up on the screen too. All right. Okay, so let's try ARP-ping. I think ARP-ping was working even at this low underclock, and it wasn't having the same problems that the HTTP server was having. So, and I think the reasoning for this is that the HTTP server is probably, like, this is kind of a hunch, but I think that what's going on is that the HTTP server is implemented largely in this thing's main loop. So it's getting blocked by something real-time clock related or something related to the PLC's main program. But ARP is all handled by the networking stack, which runs mostly in the interrupt routine. So let's get another terminal, keep this one open. Let's adjust the to-go cam. Oh, there are definitely hairless cats are kind of interesting. Sorry, there's a cat discussion in the chat. I've met some hairless cats. I have a friend who actually that cat passed away like a year ago, but it was kind of a acquaintance of mine. It was a nice hairless Sphinx cat. Tuco seems to be relatively low on the allergens. But, you know, he is a cat. Oops. All right. Did we get any of that on the scope? Okay, so I am getting responses, but the probes for 12 and 13 aren't attached right now, so let's get those on. I'm kind of doing this by trial and error. I mean, part of this is just totally cheating because I'm trying to use a logic analyzer on Ethernet. And let's get an analog channel and see what's going on here. Yeah, I think this part is actually not going to work super well with the Ethernet transformer in place, because the transformer itself, I don't know, what is this without, oh, what is this DC coupled? Because that's one of the signals I'm interested in. And that's another. And this is the receive, which I've already got on the other side of the transformer. Yeah, I think this signal has just got a weird threshold. Like, because of the, yeah, so I think this is, the way this is hooked up, the transformer has a center tap at 3.3 volts, and drivers in the SoC pull it low, but it's not giving me much of a swing here. I think just to make this a little easier to debug, I'm going to take out the transformer and just wire things straight across, like I did with the other board. So this will be the same thing I did with the little eval kit board. And this will make my Ethernet debugging situation a little easier because I can just stick the logic analyzer in on one side of this and monitor the entire link. So 13 and 12. Alright, so those are plugged in such that I should get a good trace after I take this part out. And there she is. So I think I might just force this off. I think that might be the easiest. And I don't even necessarily care that much about these pads, since I have other pads. Look at that! Yank. And yeah, so they have two sets of pads for everything over here. There's the little footprint and then this bigger footprint. So I'm just going to wire across on the bigger footprint. I'm going to ignore the center taps and just wire across the two transformer coils. So get a few pieces of wire. Oh, you can see I already used that for one bit of debugging. So let's just get a length here and then cut a few pieces to the length I want. Alright, for these cut to length, I'm going to tin one side before putting these in, and then solder the other side, and then go back and resolder the first side. Definitely using the full force of the cat hair solder composite here. Okay. How's that? Whee! Oh, that's better. That's kind of nice, actually. So if I kill that, we should just see link integrity pulses on both sides if I have the trigger. Yeah. Oh, neat. So I had been triggering this on just I think the negative side. I always forget the polarity, but the link integrity pulses are unipolar, so they only show up on one of the plus and minus lines, not both. But if I go back to triggering on the other half of that twisted pair, now we can see the link integrity pulses. And normally the link integrity pulses don't stay locked like that, but in this case, both of the Ethernet peers are running off of the same clock. So like that phase offset should be different every time I reset this, but then it'll stay pretty much constant. Oh, it's just taking a while to come up too. There we go. Man, this is going to be slow. This thing takes so long to boot. Wow, yeah. That's going to be really annoying. Yeah, I'm probably going to want to look for ways to speed this up as soon as I can. Like as soon as some of the firmware dump reveals another way in, I might want to take that. So you can see the phase randomizes. There's a lot else going on there, huh? Anyway, let's go back to ARPS and then try HTTP. Ooh, yeah. So that's yet another random phase offset. So let's try. So now you can see the ARPS mixed in with the link integrity pulses. And then if I want just the link, or just the ARPS, then I can switch this back to triggering on D14. So now I'm triggering every time one of those ARPS goes out. It's not auto trigger. And now we can see responses to what seems to be all of them, but with kind of a varying offset. If we look closer at these Ethernet packets, you can see that without the Ethernet transformer in there, we're actually just seeing the pulses that would have been driving current across the two halves of the coil in the transformer. But instead, we just see the positive and negative pulses as separate entities on the two wires. So, all right. I don't think I'm going to be able to get an HTTP request through, but let's see if we can. I also noticed that it hasn't been... Well, I haven't been noticing traffic on I2C, but let's see if we can find any that I haven't been noticing. So let's just trigger on D9 in this, or sorry, D0. It looks like nothing. We'll definitely see something if we reboot this. So, yeah, we get that packet right after reboot. Doesn't seem like much. Can I set the time or otherwise interact with the clock in a way to force it to say hello to me? Oh, the keyboard is not plugged in. Okay. Setup. Oh yeah, okay, there was another actual packet. And then something else, little. Okay, so maybe this is it polling the current time? Yeah, I saw that change a little bit. Looks like it's counting. Looks like it's doing that every second or two. And so this is while I'm in a menu, and I don't think the program's running. Am I not sampling fast enough to catch that now? It is infrequent. Peak detect. Triggered. I just want to know how frequently it's pulling the clock. Every 4.5 seconds? Interesting. Well, that alone would definitely not account for the HTTP behavior I was seeing. But let's see. I mean, this might be different depending on the operating mode of this thing. So right now the program is running. If I stop it, oh, it just pulled the time again. Yeah, this clock might have nothing to do with the HTTP server, but we can watch it tick at least, that's fun. So this seems to be the problem that we were hitting before. Can we do pings? We can do ICMP. Kind of. How is that working out? Oh yeah, those are the pings. So those are also being handled presumably in their interrupt handler by the networking stack without having to go through the main loop. Okay. Oh, I am also not monitoring power, which might be interesting. There does seem to be a lot going on this main loop that has nothing to do with the Ethernet packets. Okay, well, I think the next thing to do is to try to get this into a state where the HTTP works by speeding up the clock if we can, and then just see if I can... Oh, that's interesting. So I'm getting something. You know, I think what we were getting before when I looked at the Wireshark was I would see an HTTP 200 OK response, but then it just wouldn't start sending the data ever. So that might be what that is. Yeah. Definitely see the main loop involvement there. All right, well, clock. Let's speed up the clock. Maybe also put the clock on the scope. I've not left myself great places for getting the clock, but there's kind of one. I want the clock on the screen, especially because of the, well, all the PLLs it's going through, and you know, nothing's really designed for the frequency I'm putting it in it, so I need to keep a close eye on whether things are performing. I don't really care about voltage noise, so I'll use the alligator clip. Let's go this way over here. Okay. So there's the power on the processor. There's the clock. Okay. So we're going to do the thing where we try to raise the clock frequency as much as we can and probably have to reset the PLL and the network proxy a bunch of times. I think I got some okay results around 60 megahertz. This says it's working, but I'm going to reboot it anyway. Network restored. Pings work. Not so much luck with this, I guess. Okay, can we go higher? There we go. That is very touchy. Let's see if we can figure out why. Well, now it's okay. This might be what we want, because now it's a state where sometimes it fails and sometimes it succeeds. So when it succeeds, when is it even sending the response? And actually, this might be a good time to use that experiment I have that simultaneously reads back the web page and pokes a GPIO, because then I can trigger the scope on that. So, does that work? Oh, I had a script on this machine for that. Okay, I just copied this to the Raspberry Pi. So this command poster script. Yeah, I think this will do what I want. Let's try it once with this still set to 18, because that'll make it click. So it'll be a little easier to tell that it's working. Oh. Is that a real thing here? Yeah. It might just be called crypto. I think I used some functions in there to implement the login challenge response. All right, so trigger. I think we want 10 for that. So red, black. Yeah, pin 10. Okay. catching up on the discussion in chat. There's a lot of IoT talk. Oh yeah, there's a question, what happened to the RTC that was making things foul up last night? Well, I don't know if that's actually the root cause. Like, so now I can see what the RTC is doing, but it isn't pulling it as often as I thought it might have been. So I'm still trying to figure out what is causing these HTTP requests to sometimes work and sometimes not, so that I can try to make them work more reliably. Oh, that was the click. So why is it not exiting? Oh, is this going to be... That might be useful. Well, so my theory now is that this is going to sometimes work and sometimes not work, and what it just did was it clicked, but then it hung before returning the web page. Let's see if sometimes it clicks and then also returns the web page. Just a click. Okay, well, maybe we'll switch it back to the one that doesn't click and use this to trigger the scope. Because, yeah, I mean, I'm still largely working blind because I don't really know what the modifications they've made to the web server look like. I've got source code for the example code that I think their product is based off of, but I can only guess about how they might have modified it to insert their own stuff. Yay, so that's similar. I wonder what packet that is that we turned this on in the middle of, but I kind of suspect that might be the HTTP 200 OK. One thing we might want to do is to try to correlate the packets in the PCAP log with what's going on in the scope. I think that's our smoking gun. Ah. So check that out. Ooh, is it not going to do it this time? Let's see if that's reproducible. I don't know if you saw what I saw, but the smoking gun I was referring to was a packet on the I2C bus that talks to the real-time clock from right around the same time as this. So I think what's going on here is, I mean, I'm going to be making some conjecture here, but you can see the packet coming in. I'm going to assume that this is the last packet in the HTTP request. And so down here you can see the power waveform change, where presumably this is where it actually starts processing it. Maybe on the main loop, maybe in the ISR, I'm not sure yet. Then somewhere around here, it gets to the point of starting to kick off a bunch of asynchronous stuff in sending the response. So I think one of the asynchronous things that it kicks off is it toggles this, which would be the result of running this through the PLC program. So maybe some of this is like evaluating that program. But then at around the same time, we're also sending this packet out. So this could be HTTP OK, it could be something else. We'll want to take a closer look at that probably. Then the other thing I saw here looked like it was reading the current time from the RTC during that same operation. So one way that that might be working is during that initial phase of trying to fulfill this HTTP request, first it decides, well, what is this? Could it be successful? Do I want to send an error right away? In this case, it's like, well, this is a click command on one of those buttons, and it might return something, so it starts some deferred actions. And then up here, this is probably just that HTTP OK. Let's see if we see anything else interesting when that, well, it's going to take a while for that to go off because I think it keeps the relay on for like well, running at full speed, it's probably something like 1/10 of a second, and so now it's probably more like 1/2 a second. Let's see if we can get a more zoomed out view of this. Yeah. Okay, so it's like 1/2 a second. And it's not quite the same smoking gun. I mean, that could have been a huge coincidence, or it could have been something where it needs an accurate timestamp at that point, and if it doesn't have a recent one, it'll go request one right then. Let's try doing this a few more times and see what that looks like. You can also start to see the flow of packets here, so that'll definitely be useful side by side with the PCAP. That time it was the timestamp poll was much closer to the beginning. So this is all interesting, but I really want to know what the difference is between the working and non-working versions of this. So ideally I would have a response from this over HTTP. I wonder if I can speed up the clock anymore and still have this working. I mean, I can always speed up the clock more by taking my divider out of the system if I need to, and just going back to not underclocking it much, if at all. That's an option. The PLL is not alive right now. Ooh, that is not happy. I don't think this PLL is going to work with this input frequency. Alright, that's about as far as I can push it. That's 85 megahertz. If this doesn't at least work sometimes, then either I'll try a different test or I'll try not underclocking it. Ooh. Ooh, this is not a happy clock. Oh. This thing is also not happy. We getting a link? We getting a link? TX waiting for buffer. Really? That would indicate it thinks that it's transmitting faster than the hardware can keep up, which is weird. Oh, geez, actually, so whenever this managed to happen, actually, this is what I wanted. This is the result from command poster, which looks just like index.html, because that's what it is. Okay, let's turn this frequency back down so I'm not just glitching everything out. 82 megahertz? Can that work? Let's reset everything. Reset that. Oh, now I'm not. Yeah, I bet the clock was glitchy in some way that was not obvious, but was making the Ethernet PHY unhappy. TX waiting for buffer. need to physically power off this board? Did I give it some kind of terrible latch up? Let's unplug that. Temporarily unplug this. Reboot this Raspberry Pi just as a quick way of clearing out any network buffers that might still be full of packets. That's interesting. That's better. What did I even do? Well, pings work, but we're back at this point. Okay. Oh, let's just, I don't even have to rewire anything. Let's just program the FPGA with a straight-through program that doesn't have a divider in it. So there's that. Now, get the frequency for that on this. Yeah, 5.2 megahertz. So I'm just going to make a copy of this as a kind of dummy module. Alright, so no PLL, no divider, just this. Yay, 25 megahertz. Okay, no longer underclocked and didn't have to rewire anything major. So now oh, and now the curl just comes back right away. See, this is what's got me confused because, you know, underclocking something just changes its notion of time unless we have two different time domains that are changing relative to each other. So, and the only thing that I saw that might, well, the leading candidate for that at least was that external real-time clock chip. But now that it's working, let's take a look at how it's working so we can actually get some idea of why it was breaking before. So the curl works. Let's see if this command poster works too. Yeah, oh, that's great. So this, basically the same as grabbing index.html, but it also toggles a GPIO so we can trigger the oscope. So I think that's D10. Take the clock away for now. Nice. Oh, there we go. Nice. Oh, interesting. So you can see now so this is our little train of polling the real-time clock. And so now we're not underclocked anymore. This is real time. So it's polling the real-time clock every what it thinks is 1 second according to the CPU's oscillator, which seems about right. It's probably doing that in its systic interrupt or something like that. Then we can see the Ethernet traffic. And there's this little exchange a ways before the trigger happens, this little exchange right before, and this right after. So it could be that what's going on is like I'm back to making guesses about the main loop, but basically what this might be doing is, you know, if the main loop in this PLC is doing a bunch of things in order, whereas one of those things is evaluating the contents of the PLC program, it might be that after it does all those things, which includes pulsing this I/O, then it gets around to actually flushing out the results of this HTTP request. So when I'm not underclocking it, it just acts like it never gets around to this third section here. It does the first two, we get this pulse, but then it just never does that. But for that to have any correspondence with the real-time clock, then I can think of two, well, so I guess there are three possibilities here. One is that this has nothing to do with the real-time clock, and that's just a red herring, which is confusing because that means there's something else here that I'm not slowing down. And as far as I can tell, they're not using the 32 kilohertz oscillator that's built into the processor. There's no crystal attached to that. So one possibility is that the RTC isn't involved. Another possibility is that this is the RTC, but it's not actually it's not actually polling the RTC during this process. It's more that it uses the RTC to calibrate some internal clock to the external RTC as a reference, and by having these two things running at vastly different rates, we've caused the main loop to misbehave somehow. The other possibility is that it is just polling, and it, for example, is like this poll right here causes some deferred reaction that causes the rest of this to finish. And so that third possibility, I think we can eliminate relatively quickly by just running this a few more times. That middle one is what I'm currently gravitating toward. Like, I think this probably does have something to do with the RTC, but it might not be this direct. I also want to see what happens if we just unplug the RTC now that we have those jumpers, see if this thing even still boots and how it behaves. Interesting. So that time, that second group of network packets, that's lined up right there with one of these RTC poles. So yeah, I wonder if it's got a loop that it expects to run every second, and then like it schedules something to happen on a particular second, And then because we're running so slow, it just skips that scheduled item entirely. I wonder if that's it. Oops. Didn't mean to do that. All right. Oops. I know how to shell script, really. That's interesting, too. Well, you know, it might be approximately getting on to sandwich o'clock over here. Maybe while I'm getting a bite to eat, I will leave this running and get some video footage that I can time-lapse to get a better sample of all the different behaviors this might have. I think for that to work, I'm going to need a way to kill this when it doesn't respond. Is that a real command? I remember seeing something like this in a shell script a while ago. Yeah. Is that a thing? Can I do it that way? How much am I delaying? I'm only delaying 1 second between these. Yeah, I think I just need to zoom the scope way farther in. I think I was just getting multiple experiments on the scope, which isn't super helpful. Okay, now let's try to center the data that I care about and get a better view of the power waveform. So I want to look at the SPI later, but right now I don't really care about the SPI, so let's turn that off. And I also don't care about I don't care about reset right now. Oops. Oh, hey, Tuco, that's my keyboard. You sure are stepping on my computer all the time. Here, close the computer so it doesn't matter. I know about the cursors, dude. Okay. And let's embiggen this significantly. Well, it might be too zoomed out to really see much on the power waveform, but I don't know, sometimes these things surprise me and I look at the video afterwards and there's more of a pattern than I expected to find. What's this? I think that's the view I want. Well, he's a sweetie. Okay, well I think I'm going to leave this be for a bit and go get my sandwich. Let's see, what is next here? I mean, mostly the path I'm on right now is trying to understand how the web server and the rest of this thing's presumably main loop interact with each other. And so I've got all these elements, kind of moving parts, like the web server responding to the HTTP request with an HTTP 200, and then the web server sending back the entire response, and then the PLC program both turning on and then turning off the output, and the polling of the real-time clock. I've got all these things happening separately, and part of what I need to do now is figure out which of these things are actually related to each other and try to get a handle on how to control the timing of the web server and the GPIOs relative to each other. So that's where we're headed. And then, of course, at the even larger view, I'm trying to take a technique I'd been working on some other processors where while it's reading back some chunk of memory. So I did this in the previous video with USB descriptors. I'm trying to do it here with a web page that's stored in flash memory. I want to cause a voltage glitch at just the right point in time, such that while it's trying to formulate that response, it actually just starts giving me bits of its own firmware memory as a way of so I can use that as a way of dumping memory out of a device that's otherwise not accessible to debugging tools in order to find vulnerabilities or find hidden features or just generally evaluate a device's security. So so there's various levels of this. Trying to research this device itself is interesting, but also trying to develop a technique, especially a technique that's easy to use on other devices, is pretty interesting. So that's certainly a priority, to make something that is applicable, that I can document for other people. All right, I think this is stable enough to leave it for a bit. Thanks for joining for another bit of hacking today. I might be back later tonight, depending on how things go. But until next time. Oh yeah, one small comment. I just saw US Water Rockets in chat mention that there's a ROM bootloader in these TI parts that might be a good attack vector. That is certainly true. That might be worth looking into. I think that so far it's been looking like most of the debug features in this chip are disabled, but that certainly wouldn't stop a well-placed glitch at just the right location in the bootloader. And that has the advantage of being something that's right after power on. So it might be a bit harder to time, since I think we'll find that the processor always runs off of an internal clock during the bootloader, but it's still probably close enough to provide some experimentation. So yeah, that'll be on the stack of things to try. Happy hacking!